Welcome back to the podcast, everyone. Today, Brian and I are diving into a fascinating topic, uncertainty in scientific modeling. Specifically, we're exploring how to best quantify and report uncertainty in physical properties derived from models, a topic thoroughly examined in a recent paper by Zhang and Kitchen.
That's right, Emma. Many physical properties aren't directly measured, but rather calculated using models. Think about something like the bulk modulus of a metal. It's not something you measure with a ruler. It's a property derived from an equation of state, a mathematical model describing the relationship between pressure, volume, and energy.
Exactly. And because these properties are model-dependent, there's always inherent uncertainty. But what kind of uncertainty are we talking about? And how do we quantify it properly?
That's where things get interesting. Zhang and Kitchen highlight two main types of uncertainty, what they call model-specific and model-general uncertainty. Model-specific uncertainty reflects uncertainty tied directly to the specific model used, like uncertainties in the model parameters. But model-general uncertainty is broader. It considers how much the choice of model itself impacts the result. What if you chose a different equation of state? Would you get a completely different answer?
That's a crucial distinction. The paper uses equations of state for palladium and gold as examples, common models in materials science. They compare several approaches to quantify uncertainty: the delta method, a frequentist approach based on derivatives, Bayesian regression, and Gaussian process regression.
The delta method, in essence, propagates the uncertainty in the model parameters through to the derived property using calculus. It's relatively straightforward but makes some strong assumptions, such as normally distributed parameters.
Bayesian regression, on the other hand, offers a more holistic view. Instead of just point estimates, it provides a whole probability distribution for the model parameters and allows you to incorporate prior knowledge about these parameters.
And that's a huge advantage. However, Bayesian methods can be computationally more intensive. Both methods are what we would call model-specific. Their uncertainties are tightly coupled to the assumptions made within a specific model.
Right. Now, the really exciting part is the Gaussian process regression. The authors show this approach captures model general uncertainty. It accounts not just for parameter uncertainty within a single model but also for uncertainty stemming from model selection itself. It essentially considers the uncertainty across a family of models, averaging over potential model choices.
That's a significant leap forward. It's like having a built-in error bar not just for the measurements within a model but for the model itself. That's far more realistic in many scientific situations. The Gaussian process provides a more robust picture.
Exactly. The paper concludes that if your true model is unknown, and let's be honest, that's often the case in science, then model general uncertainty is crucial. We need to consider uncertainty from the model choice itself. It's not simply about how much our parameters might vary but also about how the model choice influences the result.
So, the key takeaway is that understanding uncertainty in derived physical properties goes beyond just considering the specific model you use. We should always aim for a more complete picture, acknowledging the inherent uncertainty in model selection itself. And Gaussian processes are presented as a powerful tool in this pursuit.
Absolutely. In many situations, model general uncertainty is the more significant factor to consider, and Gaussian processes allow us to quantify it effectively. Thanks for joining us for this discussion, Brian. Until next time.
My pleasure, Emma. A fascinating area of research. Thanks for listening, everyone.